All right, people. So today we are covering a limiting reactant. Right now, chemical reactions are, first of all, they're never super efficient. You always have some waste. All right. I really enjoy cooking. Right, cooking is one of my favorite things to do. But every time I cook, I'll always have something a little left over. Right, I'll chop up an onion or two because I don't want to have. I don't want to run out. Oh, look, special guest. Hi, Pika. Say hello. Say hello, Pika. Pika, don't be rude. All right, whatever. Anyways, every time there's a chemical reaction, there is something that is left over, and there is always something that runs out first. So it is very, very important to know that when it comes to manufacturing, whenever you want to produce something on a large scale, you want your most valuable things to you want to be as efficient as possible. Really, you want to be as efficient as possible. So it's important to know how much stuff you're going to make, and you always have something that runs out. Now I know I have some definitions around here somewhere, right there, but you don't need these right now. You should have already written them down. But let's take a look at this. So using the last problem, so hydrogen gas can react with nitrogen gas to produce ammonia gas. So you should already know how to write a formula. You should know that H2 gas reacts with nitrogen gas to produce ammonia gas, NH3. This is a very important reaction. This is the Haber process. Now, we need a balanced formula. So there's two nitrogens here. And then, so let's say we put two nitrogens there. But now we have 6 hydrogens. So we need 6 hydrogens over here. So now it looks balanced. Now, we have a balanced chemical equation. Awesome. You always need that. Now, when they're asking what is the limiting reactant, what they're asking us is to do 2 problems. To start the problem with one substance and compare it to the same problem, but starting with another substance. So let's do that. In this problem, they told us we have 10 grams of hydrogen gas, and they told us that we have 10 grams of nitrogen gas. And they want us to figure out which one's going to run out first. I should write darker, huh? I like that. Ooh, that looks so much better. All right. So what do? Well, we want to find the mass of ammonia. So in both problems, we're finding the grams of NH3. We're finding grams of NH3 in both problems. So how do we do it? Well, we have grams of H2. And once again, we should always go to moles. All right. Now, the molar mass of H2, since there's 2 hydrogens, 2.02 grams of H2. Now over here we want 1 mole of nitrogen, and then, well, nitrogen is 14.07, so let's say 28.14 grams of nitrogen. All right, now we don't want moles of our starting substance, we want grams of our ending. So now that we're at moles, right, we got to go to moles of something else. So we need that mole ratio. So we need to compare H2 and NH3. In the other problem, we're comparing N2 and NH3. All right, so different ratios. Let's check them out. So we need 3 moles of H2 for every 2 moles of NH3 that we make. Hello, Pika. Now, ooh, don't scratch me, girl. Don't scratch me. Don't scratch me. You gotta cut those nails. Now we got 1 mole of N2 for every 2 moles of NH3. Pika, you want to sit on my lap? Let's go. Thank you, girl. All right. So now we are at, we're at moles of NH3. Let's convert that into grams. Whoa, whoa, whoa. All right, Pika. Special guest right here. All right. Don't be shy, Pika. Don't be shy. All right. So let's check this out. We have we're trying to go to moles of NH3. We're trying to go to grams of NH3. So we need the molar mass of NH3 on the top. And so nitrogen is 14.007. And hydrogen is 1.01. So there's 3 of them. So 3.03 plus 14. Let's just say 17.037. And let's do that with both of them, 17.037, because it's the same mass. No need to calculate it twice. It's literally the exact same thing. So limiting reactants is always 2 problems. It's always one reactant going to the product, and then the other reactant going to the same product. So the second half of the problem, I don't know if you notice, but the second half of the problem is the exact same thing. All right, the exact same thing, and it always will be. It always will be. All right, now let's do the math for both. Start off with 10 grams, divide by 2.02, multiply by 2, divide by 3, and then multiply by that 17.037. I'm sure my mass is off for nitrogen, but who cares? Who cares? Someone's going to be like, this guy doesn't even check his work. He doesn't even do this right. It doesn't matter. It's the concepts that you're getting, okay? It doesn't matter if the number is exactly correct. So this right here is 56.2. That's it. 56.2 grams of NH3 that's made. Now let's check out the other one. 10 divided by 28.14 multiplied by 2 multiplied by 17.037. And that tells us that this can only make 12.11 grams, or 12.1 grams, because we only have 3 sig figs here, so we got to give 3 sig figs. So which one is the correct answer? Well, remember what we're trying to find out. We're trying to find out which one runs out first. So which one of these do you think is going to run out first? The one that can make 56 grams, or the one that can only make 12.1 grams? Since nitrogen can only make 12.1 grams, that's as much as we can make. That's as much as we can make. So that is our limiting reactant. Nitrogen runs out first. All right. So which is the limiting reactant? I would say N2. Which is the excess reaction? H2. How much excess do you have? That's a very, very good question. How much excess do we have? How much leftover hydrogen will we have to use for other chemical reactions? How do we do that? Very simple. You do a third problem. We start off with 10 grams of nitrogen, and then we do the exact same thing. So 1 mole of N2, except instead of trying to go to nitrogen, what are we trying to find now? If we want to find out how much excess we have, well, we're trying to find out how much hydrogen we have. Oh, sorry, Pika. All right, so 28.14 grams. I have a feeling this mass is wrong, but it's okay. Pika's here. So instead of going to ammonia now, what we're going to go to is we're going to go to hydrogen. So we need the mole ratio of N to hydrogen. So we know it's 3 moles of hydrogen for every 1 mole of N. And then what we need, hold on, Pika, is the grams. So 1 mole of H2 is equal to 2.02 grams of H2, the molar mass, right? We're trying to go to grams of hydrogen because we want to know how much excess we have. This is going to be a little bit of a long video, but it's okay. So 10 divided by 28.14 times 3 times 2.02, and we get 2.15 grams of hydrogen. So 10 grams of nitrogen will react exactly with 2.15 grams of hydrogen. So everything else is left over. So if you get 10 grams, because we have 10 grams of H2, but only 2.15 grams of H2 are going to react, so we're going to be left with about 7.85 grams of hydrogen. This is all mental math, so if I mess up, I mess up. It is what it is. All right. So that right there is the excess hydrogen. So that can be used for other chemical reactions. Now, sorry for all my ugly writing up here. I know I do a lot of scribbles. I'll work on that. So shut up and don't point it out. Don't be like, Mrs. Sanchez, you write so ugly. You write so ugly too. Sorry, not. There's probably like 3 of you that do. All right, but anyways, that is how we do limiting reactants, right? Oops. So that's how we do limiting reactants. What I'm going to show you is how do we calculate something called the percent yield, or actual yield, or theoretical yield, right? Let's check this out. It seems a little bit long for that video. Maybe I should do 2 parts. I'll do 2 parts. Peace out.